Swayam Prabha. Digital India. Educated India.
We will look at the VGG network, specifically the VGG 16. So, VGG stands for the Visual Geometry Group at Oxford University. So, this particular network was entered into the 2014 ImageNet challenge. Okay. So, it had 16 weight layers, okay, 16 layers weight. This one we are looking at as 16 weight layers. They also had another version which 19, VGG 19, we had 19 weight layers. So, the design of this is very similar to LeNet and AlexNet, okay, except that they have made this a little bit more systematic. So, we will see what the systematicity is here. So, we saw one of in the earlier videos we saw that it's best that as we go deeper into the network we increase the size of the depth or the number of feature maps increases. So, it becomes wider, network becomes wider, okay. So, that was incorporated here. They also stuck to one filter size 3 cross 3. This is the smallest filter size, smallest meaningful filter size. So, 3 cross 3 gives you you can also do 1 cross 1 convolution, but of course we need a receptive field. So, 3 cross 3 is the small. They stuck to 3 cross 3 filtered throughout all the layers. There are a lot of parameters, about 130 to 140 million parameters depending on which network you are looking at. Once again we will just walk through the network briefly and then we will see what are the advantages given by this network. So, if you see the input again same 3 channel RGB image size 224 cross 224. So, the first layer has 2 3 cross 3 convolutions in succession followed by a max pooling layer which reduces the size of the feature maps to 112 cross 112, and each of these 3 cross 3 convolution layers had 64 feature maps followed by another set of convolutions and max pooling, so on and so forth till we get to the these 2 layers which have again 3 cross 3 convolution, but this time 3 in succession, 3 of them in succession if you see here, followed by again a max pooling. And here of course these are rasterized and made into a fully connected layers here, these 2, and the output is a 1 of 1000 classification. Now this has if you look at this we will see that this is a block, okay. This is one of the earliest networks to introduce this kind of concept. We will see another network where most networks now use this. So, this is a block of convolutions. So, basically instead of your layer is now being replaced by a bunch of convolution layers, okay. A sequence of layers is now used as one layer. So, in between these 2 convolution layers there is no max pooling, but the non-linearity is still there. So, 3 cross 3 non-linearity and then a 3 cross 3 non-linearity, okay, that is the sequence. Again in this case 3 successive non-linearities of are applied following the convolutions. So, what does this provide in terms of an advantage? So, if you look at a succession of 3 by 3 convolutions, one is the non-linearity leads to greater discrimination, okay. Seeing that we have looked at other classifiers. So, if we have very non-linear features we expect that at some point the classes become linearly separable, that is, but then how do we incorporate this here in the network is to have a succession of non-linearities, hopefully giving rise to better discriminatory power in the network. The second advantage is in terms of the receptive field, okay. So, the authors also mentioned this, that if you look at this particular or we can just come here and look at this. For instance, if you look at these 2 3 cross 3 convolutions, okay. So, this is one convolution layer with 64 feature maps, 3 cross 3 convolutions, again 64 3 cross 3 followed by another set of 64 3 cross 3 convolutions, okay. Now, if you look at the receptive field of this layer of this block, so the first one as a receptive field of 3 cross 3. Okay. So, that gives rise to 64 feature maps, right. So, now if you look at the second, if you look at the this is the first one, if you look at the second one, okay, the filter kernel size is 3 cross 3, okay, but the receptive field on the original image. So, we are looking at the receptive field of this particular layer on the input side, okay. So, the receptive field for this one is 3 cross 3 and for the second it becomes 5 cross 5. It is not too hard to see, because if you look at the second convolution, the feature maps in the second convolution layer, okay, we have 3 cross 3, okay. So, if you look at this particular activation in the feature map, then it itself is a result of a 3 cross 3 convolution. So, this itself is a result of a 3 cross 3 convolution, right. So, you have 1, 2 and a 3 here, right. So, this particular feature map in the second 3 cross 3 convolution layer itself is the output of a 3 cross 3 convolution from the previous layer. So, this is looking at 3 1 2, let us say. So, then we see that all around we will have to add one more row and column, okay. So, its receptive field on the input is actually 5 cross 5. So, similarly, if you look at the succession of 3 convolution layers, so the the final receptive field for this the receptive field of this particular convolution layer would correspond to a 7 cross 7. You can verify that on your own. So, what does this provide in terms of computational gain? That is what the authors claim, or the authors claim. That is what it that is the computational gain you get from this, is that if you want to do a succession of 3 cross 3 convolutions, 3 of them, the number of computations involved to produce one element in the output feature map is much lesser when compared to if you just do a 7 cross 7 convolution, okay. So, this is and at the same time you have a larger receptive field on the input. Sometimes it is desirable, in many cases it is desirable to have a larger receptive field, so that you get more of the context in the image into your activation maps. But doing a much larger convolution, using a much larger convolution means that the number of computations increase. So, one advantage of using a succession of 3 by 3 filters, convolution layers, instead of just using a filter with a larger receptive field, is the savings in the number of parameters. So, for instance, if you had used 7 cross 7 filters on C channels, then the number of parameters would be 49 C squares. On the other hand, if you would use a succession of 3 convolution layers to get the same receptive field with 3 by 3 filter sizes, then the number of filter sizes would be about 27 C square, okay. So, this gives rise to this decrease in the number of parameters actually. This might not be very obvious, but you have to do the computation to figure out, because if you have C input channels, then so how do we get this number? If you have C input channels, then the size of each filter would be, if you use a 3 cross 3, the number of elements in which each filter would be 3 cross 3 times C, right. And then if you have C output channels, then we have one more C outside, that is the total number of parameters, okay. Then we have a succession of 3 layers with 3 cross 3 filters, so 3 times that, okay. So, this is how we calculate the number of parameters in when we use a succession of 3. Of course, the similar calculations for 7 cross 7, okay. So, VGG net by using the succession of convolution layers with very small filter sizes, but of course, the number of parameters is much higher than the AlexNet, but the results were much better. It is about 7% in the top 5 7% error rate in the top 5, which was in fact that was not the winning, it was not the winning entry, but it won in other categories in the challenges, localization, etc. But the error rate was still pretty good, was around 7%. Okay. So the winning network was actually the Inception network or Google Net from Google. We will see much more about it in the next videos. In this video, we will look at Google Net. The basic building block of this Google Net is the Inception module. This is again a 2014 winner of the ImageNet challenge. So let us look at the basic building block of the Inception module. So for instance, we had for the VGG network that we saw in the previous video, the basic building block was a block of convolutional layers using very small filter sizes. And if you looked at, remember, if you recall AlexNet, now AlexNet had variable filter sizes. So each first layer had 11 cross 11 filters, and then we had 5 cross 5 filters, and then we had 3 cross 3, and then a fully convolutional network. Okay. So the Inception module incorporates both these concepts, sense that every layer has all possible filter sizes. So they built a block, a convolution block, which had multiple filter sizes, and they let the network, the backprop, the learning through which the network learns, and let the backprop decide which weights to update based on your objective function. So let us just quickly look at this Inception module. So if you look, there are two images. So this here is what the authors of the Google Net paper call the naive implementation, and this is the actual implementation that they have followed. So what is the difference? So we have an input feature map. Okay, this is the thickness of the feature map right here. Let me use a different color, which will highlight this, right? This good. So this is the thickness of the feature map, as I have pointed out. Okay, the size, some k feature maps, and we have 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3 max pooling also applied to these feature maps. The outputs of each of them are taken and concatenated. So they are concatenated across that way. Okay. So again, this means that we have to do the convolutions so as to get the same sized feature maps from each of these convolutions. So they are all 0 padded accordingly, and to get the correct size feature maps so that they can all be concatenated. As you will see, doing this has a problem, because the number of computations becomes huge. Okay. So if you just, so this is the naive implementation. So but doing it this way, doing implementing the block, the Inception module as they call it this way, has issues in terms of the number of computations involved. Okay, it becomes huge because we have large filter sizes 5 by 5 also in that. Okay, we can also use, I think it is possible to use 7 cross 7 also, but the authors of the Google Net Inception module just stopped with 5 by 5, probably worked very well for the ImageNet challenge. Okay. So what is the better implementation? The better implementation is to use 1 cross 1 convolutions to reduce the size of the filter maps. In the sense, when I say size, in this context it is the depth of the feature maps. Okay. So if you have, so if your input layer has, let us say, if your input layer has 28 cross let us say 192 inputs, okay, so many feature maps. So in this case, let me write it down here, so that this is where we are going to do the 1 cross 1, 192. Okay. So we would use the 1 cross 1 convolutions to project this number of feature maps to a smaller number, to a smaller volume. So what I mean by that, we know that, as if you recall, we know that 1 cross 1 feature maps preserve the size of the feature maps, in the sense in plane. The x, y size of the feature maps are preserved, but we can use the 1 cross 1 convolution to reduce the depth of the feature map. So that is pretty typically precisely what the Inception module accomplishes. So if you have a very large, in the sense of a very wide volume, so so very large number of feature maps in the input volume, you would use this 1 cross 1 convolution to bring it down. So, for instance, in this case let us say we take the 1 cross 1 convolution before the 5 cross 5, we can use the 1 cross 1 convolution to reduce the size of feature maps to 28 cross 28 cross let us say 16, okay. And then we can output let us say from the 5 cross 5 convolutions we can output 28 cross 128 feature maps, okay. So, just to recall how this is done is by defining 16 1 cross 1 convolutions. Of course, 1 cross 1 convolutions act across the volume, across the feature maps. So, you can also question whether this would lead to loss of information. So, this seems to be a parameter they have tweaked, the number of feature maps here. This has to be done by some kind of cross validation to see which is the most optimal, okay. So, this 1 cross 1 convolutions prior to doing the larger convolutions with larger convolutions in the sense of convolutions with larger filter sizes. So, the 1 cross 1 projects the input volume to a smaller dimension, and then subsequently you use 3 cross 3 convolutions to put them back, okay. So, this is what is referred to now as bottleneck layers, okay. So, you shrink the size of the feature map, that way it works. Similarly, for the max pooling also you can do because max pooling would in most cases preserve the size of the feature maps, the depth of the feature maps that is, and you can use again 1 cross 1 convolutions to reduce the size, okay. So, this was the two of the big innovations in Inception module. So, instead of just, so if you saw in VGG that each block they divided the network into blocks. So, each block had a succession of convolutions. So, in this case for Inception module it incorporates multiple convolution kernel sizes, just like in AlexNet we saw that they use 11 cross 11, 5 cross 5, 3 cross 3, but in this case it is 5 cross 5, 3 cross 3, 1 cross 1 and a max pooling layer all in one module. And we also use this bottleneck 1 cross 1 convolutions to project the input volume to a lower dimension in terms of the depth of the volume before we do the 3 cross 3 and the other convolutions with higher filter kernel sizes. So, we just look at the network. This had about 22 layers with weights, and so there was an initial set of convolutions and max pooling, okay, which reduced the size of the input to 28 cross 192. So, the input as usual was a 224 cross 3. It was followed up by a sequence of convolutions and max pooling, to get it to 28 cross 192, and then that was used as input to the inception layers, sequence of inception layers followed by max pooling, again a sequence of inception layers followed by max pooling, so on till we have the typical output layer with 1 of 1000 activations, okay. So, it had so they have labeled the inception modules as 3A, 4B. This was the, if you read the paper, I urge you to go read the paper where see that they have labeled each of these convolution, the inception modules by 3A, 3B, in this case 4A, 4B, and there is the corresponding table which tells you how the computations are done in that particular module, okay. So, we will just walk through one inception module, that is 3A, and see how the number of the savings in the number of computations by using a 1 cross 1 bottleneck to reduce the size of the field, reduce the number of feature maps. So, this is a 22 layer network, but then it had very few parameters, about 5 million parameters. Okay. And it won the 2014 ImageNet challenge with a top 5 error rate of about 7%, okay, slightly better than VGG, but with much lesser number of parameters, okay. So, this was considered this again is one of the networks which have it's very small net, very deep, but in the terms of number of parameters very less number of parameters. We contrast to let us say AlexNet as well as VGG has VGG 16 had 138 million AlexNet had 60 million parameters, but this only had 5 million parameters. So that is weights in the network. Okay. So, we will look at this Inception 3A right here, which takes as input 28 cross 28 cross 192, and the output is I think 28 to 56. Okay. So, just look at it. So, we reproduced a piece of the table here. I urge you to go back and look at the table. So, this is the output size of the max pooling layer, which feeds the as input to the Inception. This is the input to the Inception module 3A, and this is the output of the Inception module 3A. Okay. So, it has 64 1 cross 1 convolutions. So, we saw that if you will go back and we will write it down there just to see, and then it had 96 3 by 3 reduce in that table means the number of 1 cross 1 convolutions done, the 96 feature maps were produced by the 1 cross 1 convolutions prior to doing the 3 cross 3. So, you would produce 128 feature maps with 3 by 3, again 16 1 cross 1 feature maps produced by the 1 cross 1 convolutions, following by 32, okay, and then 32 from the max pooling layer. Okay. So, the output of the max pooling layer. If we go back, so if you recall some of these numbers, so we would do here. So, what it means here is the reduce is basically here. So, prior to 3 cross 3 we would have 96 feature maps here, and prior to 5 cross 5 we will have 16 feature maps there, and then the output of the 1 cross the max pooling would give you we saw 32 feature maps. Okay. So, and if you look at the output of the 3 cross 3 convolutions, I think this has about, if we can go back and look, I don't want to go back and forth again. So, the 3 by 3 produced about 128, okay, and the 5 cross 5 produces 32, right. The pooled projection layer produces another 32, this is a max pooling layer, and the 1 cross 1 convolution itself produces 64. Okay. So, this is from the 3 cross 3. Of course, there is 96 coming into this, if I am not mistaken. Yes, the reduce is 96 and the reduce is 16 here. So, this is the 1 cross 1 convolution, this is the 3 cross 3, 5 cross 5, and for the pooled projection there is nothing. For the other one, there is a 1 cross 1 convolution, this is directly from the input. These two are from the input. Okay. So, the hash 3 by 3 cross 3 reduce is basically the number of feature maps produced by the 1 cross 1 convolution. Recall that, I will once again back here. Recall that the 1 cross 1 convolutions are done prior to the 3 cross 3 and the 5 cross 5, and the 1 cross 1 convolution following the max pooling. Okay. There is nothing before, then there is one plain 1 cross 1 convolution layer. Okay. So, which is what we have here. So, this is 64 1 cross 1, 64 feature maps produced from 1 cross 1, 96 by the 1 cross 1 prior to the 3 cross 3, and then the output from the 3 cross 3 is 128, and the output from the 5 cross 5 is 32, but prior to that you reduce the dimension to 60. Okay. So, what is the savings in terms of number of computations? So, if you look at the following the output of the max pool, which is the input to the Inception module, is 28 cross 192. Now, if we directly do 192 3 cross 3 convolution, of course, then the size of the number of parameters in every filter is 3 cross 192, and then we produce, let us say, 128 feature maps, that is 28 cross 128, then the number of operations would be about 173 million. Okay. Now, if we do let us do the 1 cross 1 projections into a smaller volume. Now, if we do that, then we produce 96 feature maps following the 1 cross 1 convolution. Okay. And then we follow it up with the 3 cross 3 convolution to again produce 128. So, we have to do this calculation here for the 1 cross 1 convolution. So, the easiest way to this is again very easy to write it down. I will write this down for the 3 and then the okay. So, if you were to do 3 cross 3 convolutions to produce 128 feature maps of size 28 by 28. So, the number of elements in the output feature map or the number of activations in the output feature map is so much, right, and then for each output activation we have to do how many computations, 3 cross 3 cross 192, sum of products, right. So, 3 cross 3 cross 192, that is pretty much what you see there, okay. That comes to 173 million. You can repeat the calculation here for this one too. So, the output feature map here for the 1 cross 1 convolution is 28 times 28 times 96. This is the total number of activations produced. For each activations we have to perform 1 cross 1 cross 192 multiplications, okay. So, that is what we have here, and then similarly for the 3 cross 3 convolutions we produce 28 cross this plus 28 cross 128, right, and for each one of these activations we have to perform 3 cross 3 cross 96 multiplication. So, that number is here. So, if we add, you see that there is a reduction in the number of computations that you have just for this one particular feature map, set of feature maps, okay. So, this was the innovation behind the Inception module. So, it does two things. It lets the network decide which feature maps are more relevant based on the back propagation or the optimization. At the same time, as we saw earlier, again even with the VGG net we saw that using larger receptive fields means that the number of parameters increases and number of computations also increased correspondingly. So, that is solved by using this bottleneck layer using 1 cross 1 convolution, where 1 cross 1 is used to project your feature maps to a smaller dimension. Here the reduction is along the depth of the feature maps, so the volume becomes smaller. So, we will look at the Inception 3A layer. So, the table is reproduced from the paper, it tells you the number of 1 cross 1, 3 cross 3 convolutions, etc. in every layer, okay. So, let us just go one layer by layer. The input to the Inception 3A layer is of size 28 cross 192, it's a layer. The output has same size 28 cross 256, okay. So, now it has number of 1 cross 1 convolutions is 64, so there are 64 here, okay. The hash 3 by 3 reduce refers to the number of 1 cross 1 convolution maps produced by the 1 cross 1 convolutions preceding the 3 cross 3. So, which means that this 1 cross 1 convolution layer will produce 64 feature maps of the same size, 64 feature maps, and the 3 cross 3 convolutions will output 3 cross 3 will output 128. So, those are the two. The hash 3 cross 3 reduce here refers to the convolution layer 1 cross 1 convolution layer preceding the 3 cross 3 convolution, okay. So, it refers to this one right here. So, the number there, the number of feature maps produced as output there is 96, okay. These serve as input to the 3 cross 3 convolution. So, the 3 cross 3 produce an output of 128, okay, which is concatenated there. Similarly, the hash 5 cross 5 reduce refers to the number of feature maps from the 1 cross 1 convolution, that is 16, and the 5 cross 5 itself produces 32 feature maps. The pooled projection layer produces 32 followed by 1 cross 1 convolution. So, that remains fixed in this case. So, the total number is, if you add these up, if you add 32, these numbers, these are the, so if you put these together you get about 256 output feature maps. So, this is just for one inception block, okay. So, you can work through the table in the paper and see if the calculations are consistent with the structure that I showed you earlier, okay.